All right, so in this video, we're going to be talking about the growth and decay models, but we're going to be specifically focusing even more attention on compound interest formulas. But we have these growth and decay models, and we talked about them in the previous video where, sometimes you have a percent increase and sometimes you have a percent decrease. All right, and so like you might be investing money and you're going to earn interest, right? Or you might be selling a car and it actually may go down in value, which is called depreciation. But here, what happens if you're a business owner and you're like, okay, I want to open up a business in Locust Grove? Well, before you open a business here, you would probably be interested to know what's going on with our city. Is our population going up or is it going down? Like, are people trying to leave Locust Grove, or are we showing growth in our city? Are we, growing? Because if you're going to open a business, you may not want to open a business in a place where people are trying to leave the city, right? Because you're trying to make money. And if people are leaving, then you may not make as much money. But if you have a growing city, then you have more potential to, of course, make more money, right? So if we're looking at these different growth and decay models, these are just samples of equations or functions that would represent a model. And you might want to figure out, well, do I have growth or do I have decay? Should I expect my amount to go up or should I expect my amount to go down? All right, so what you need to understand when you look at these different models is any base, all right, so any base that is raised to x, if it has an x, or I'm sorry, if the base is greater than 1, then that's an example of exponential growth. All right. And then if you have an x value, or I'm sorry, a base value that is between 0 and 1, so really less than 1, then you're going to have exponential decay. All right. So we need to talk about, well, what's a base versus an exponent? All right. So I kind of use the whole cheerleading stunt analogy. My daughter is a cheerleader, so she's a base. Thankfully, she's not a flyer. All right. But a flyer is the one that's up in the air, right? The base is the one that's down on the ground holding up the flyer. All right. So in this case, we're not talking about cheerleaders. We're talking about numbers and, things like that, right? And variables. So in this first problem, this 1.05 is my base and this x is the exponent. So that's the portion of the equation that we need to look at in order to determine growth or decay. All right. We don't really care about the 2 for this, at least, okay? So 1.05 is greater than 1, so that would be an example of growth. All right, so then if you look at the second one, we don't care about the 540, we don't care about the plus 1, we care about this piece right here, because that's my base and it's holding up the flyer, it's holding up the exponent. All right, and that 0.92 is less than 1, so that would be an example of decay. All right. The third one, we look at the 3/5 x. Well, 3/5 is a decimal, it's 0.6. Well, 0.6 is less than 1, so that is an example of decay. The next one, we have the 7/5 with an exponent of x. Well, 7/5, think about what that is as a decimal. All right, 7/5 as a decimal is 1.4. Well, that's greater than 1, so that would be an example of growth. All right, well, then we get to this one right here, and we are exposed to something new. All right, most of y'all are not familiar with E yet. All right, so at the top of your paper, think about pi. Pi has a numeric value of approximately 3.14, right? Well, E also has a numeric value. E is approximately 2.71828, something like that, all right? But 2.7-ish, all right? So E has a numeric value as well. There's actually a button on your calculator for it, and the button is right here. See how ln is right here? And right above the ln, it says e to the x. So you get that by typing second ln. All right, so second ln, and you'll notice that it populates an e. Well, if I want to know the value of e, I can just raise it to the first power because that will give me the value. All right, and it's 2.7, 1828, 1828, blah, 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 blah. All right, so E is a numeric value, all right, not just a letter. All right, so kind of like pi. All right, so when we look at this problem here, whoops, then we have E to the X power. Well, E, if E is 2.7-ish, then that would be an example of growth. All right. Well, there's this third bullet right here. It says caution. All right. And the reason why it says caution is because it says that you don't need to forget about negative exponents. All right. So remember, you have the negative exponent rules with your properties of exponents. And the little trick we learned in class is you need to turn that frown upside down. All right. So when we look at this right here, 2 is my base, and it makes you think it's growth, because 2 is greater than 1, right? However, because we have a negative exponent, we need to remember that really that's going to flip. It's going to turn that frown upside down. So instead, this would be the same thing as 9 times 1/2 to the positive x power. And the 1/2 is an example of decay. All right. So ultimately what happens is when you see that 2, you think growth. But you also need to look at the exponent. If the exponent's negative, you need to be like, just kidding. I thought it was growth, but negative exponent, nope. Turn that frown upside down. It's going to make it decay. And on the flip side, if you see something that looks like it's decay, but there's a negative exponent, then you're going to be like, oh, just kidding. It's going to end up being growth. Why? Because you got to turn that frown upside down. So if you look at G, we're looking at the 3 to the X. 3 is growth. X is okay because it's positive. So this would be an example of growth. For H, we have E to the negative X. Well, we've already learned that E is a numerical value greater than 1. It's 2.7-ish, right? So right away, I'd be thinking growth. But because of that negative exponent, I'm like, nope, just kidding. I think it's growth, but no, it's not. It's really going to be decay. And that's because when I turn that frown upside down, this would be 1 over E to the positive x power. And 1 over E, 1 divided by 2.7-ish, is going to give me a decimal less than 1. All right, and then the last one, we're looking at the 2/5 to the negative x power. Again, I think it's decay, but then it's like, nope, just kidding. It's what? Going to be growth. And the reason why it's growth is because it would be 230 times 5 over 2 to the positive x, because we would have to turn that frown upside down. And 5 over 2 is 2.5, and that would be an example of growth. All right, so again, you're going to have some of these different models, and you're going to have to determine, is it growth? Is it decay? All right, just by looking at it. So make sure you know how to find the base and the exponent that goes along with it. All right. So that's how we can determine a growth and a decay model. All right, so that brings me to page 7, all right, which is our compound interest formula page. All right, so we have 2 different compound interest formulas. One of them is like compounded monthly, quarterly, and things like that. So you'll notice that there's this little chart right here, and N is a part of the formula. So this chart tells you like those N values, all right? And then this right here tells you what all these different variables stand for ultimately, but we're gonna go through them with our example as well. All right, so what you need to understand is that, you know, you can deposit money into a bank. Well, a bank is going to give you some interest on your money, all right? Like if it's in a savings account, for example. All right, now in these problems, it's using 9%. Just so that you know, that is not realistic. If you find a bank that's 9% interest, like let me know, okay? Because that would be fantastic. All right, but that is not the case. Usually you're lucky if it's 1%. It's usually like a decimal, all right? But nonetheless, I put my money into a savings account. Well, how that bank compounds it is going to be important, because I want to make as much interest as I can, because interest is money that I'm getting back, all right, that it's extra money for me, right? I'm making money off of my money, all right? So I need the most that I can possibly get. Well, my personal bank, like I have a savings account, my personal bank compounds it quarterly. Every quarter, 4 times a year, because there's 4 quarters in a year, like 4 seasons, 4 quarters in a dollar, 4 quarters in a football game, every 3 months, because that's 3 plus 3 plus 3, there's 4 of them, right? So every quarter in my bank account, I'll see a line item that says interest, and it has some other stuff, but there's this little bitty amount that they add to my account. And for me, because I'm not like super wealthy, I mean, it's not like a whole ton of money. Okay. But hey, every little bit helps, right? It adds up. Okay. At least I'm getting something. All right. But some banks may compound monthly or something like that. And so depending on what they compound, then that's going to impact how much money you're making. All right. So when you look at these 3 examples, all 3 examples are the same exact scenario. All 3 examples is a person investing $6,000. They're investing $6,000 and they're going to leave that money in their account for 12 years. So all of it is 12 years. And all 3 examples have an interest rate of 9%. All right, all of them, but they're all compounded differently. All right, so this first one is compounded annually. The next one is compounded quarterly, and the next one is compounded weekly. All right, so we have 3 different scenarios. Well, really the same scenario, but 3 different types of compounding. All right, so all of those, because they say compounded annually, quarterly, weekly, monthly, daily, that type of thing, is going to use this compound interest formula. All right, so when you look at the values at the top, the A is just how much money you're going to have in your account after that set amount of time. Like, well, if 10 years go by, well, how much do I have? All right, P stands for principal. In this case, that's going to be our starting amount. All right, or however much money you invest. In this case, $6,000 would be the P value. All right. That could be like if you buy a house, well, how much did you finance? If you buy a house for $200,000 and that's how much you get a loan for, then $2,000 or $200,000 would be the principal amount. All right. Now, 1 is always going to be there. That just represents 100% of your initial value. The R stands for rate. Remember, we've been using rate as a decimal. So like 5% is not 0.5, it's 0.05. So be careful. N you see in 2 different places. N comes from this chart right here. And N represents, well, how many times does that happen a year? So if it's compounded monthly, well, then how many times is it going to be compounded? Well, how many months are in a year? 12. That's why N is 12. If it's compounded weekly, then every week, well, how many weeks are in a year? 52. That's why N would be 52. Quarterly, 4 quarters. Annually only happens 1 time a year. So that's where these N values are coming from. And then T represents the time, so number of years. All right, so that's where all of those values are coming from. So now let's put these numbers, these values into our formulas. All right, or into our one formula. So for this first problem, P is $6,000. So we're going to have 6,000 times 1 plus my rate is 9%, so 0.09 over my N is already identified. It's 1 because it's annually. My N is still 1. My T is 12 years, so T is 12. So times 12. So I'm going to show you that in your calculator because you do want to make sure that you type it correctly. All right, so we're going to type 6,000 parentheses 1 plus, now this is a fraction, so I'm going to use N over D, 0.09 over 1, and then see how it's blinking? It's like, get off of me. Okay, so I'm going to arrow off to close off my parenthesis. Now this is an exponent, so be careful. So I need to raise it and put 1 times 12. And when I do that, I get $16,875.99 because money is dollars and change, right? Dollars and pennies or whatever. So we need to keep 2 decimals. So I'm going to round that 8 is going to make that bump up to a 9. All right, so almost $17,000. And remember, I told y'all this is not realistic. You're not going to find a bank that's going to give you a 9% interest rate, okay? Not a legit bank, let's put it like that. All right, so if we look at the second problem, same thing, right? We have our principal, we know it's for 12 years, we know our rate's 9%, but this time it's compounded quarterly. So I'm going to set it up the exact same way, but instead of putting a 1 in the denominator, I'm going to put a 4 because n is 4. And then n is still 4, and then time is 12 years. All right, so I'm going to put that in my calculator. The only thing that changed was the point, I'm sorry, not the point, but the 4, because 4 quarters in a year. So let me clear it out. 6,000 times 1 plus n over d, 0.09 over 4. Close it off, raise it, 4 times 12. And we get $17,457.84 if I round it. So significantly more, right? So would you rather have your money in a bank that compounds annually, or would you rather have your money in a bank that compounds quarterly? Well, definitely quarterly, because that's going to give me more money. Okay, so even though this percentage is not realistic, you can at least see that the amount goes up. Okay, so if it's my money, I'd rather it be quarterly than annually. Now, typically banks are not going to have weekly. Sometimes they'll have monthly, just depends on the bank, but we're going to go ahead and do this one with weekly. All right, so I'm going to pause just for a second. I'll freeze my screen, and I want y'all to try this problem so that you can see if you're doing it on your own. So I'm going to kind of freeze my screen while I write, and then y'all can pause the video and try it out. All right, so hopefully you paused me for a minute and tried that on your own. So I went ahead and set this up. I can't really pause the recording, unfortunately, so we just had to like wait for it to go by. All right, so, but when I try this out, I got $17,651.59. So again, I made even more money. So if I could find a bank that would compound weekly, then that would even be better, right? And we didn't do monthly, but monthly would actually be better than quarterly as well. So the reason why this scenario happens 3 times is because I'm trying to get you to see that the more often you compound, the better it is for you. All right, now not for the bank because they're giving you money, right, for interest, but for you, it's better. Now, if you are, you know, having a loan and you're the one paying the interest, then you don't want it compounded a whole lot. You know what I mean? Like you only want it compounded like quarterly or annually or something like that. You don't necessarily want it monthly and all that kind of stuff. Okay, but you'll find that when y'all start shopping around for, you know, like if you want to buy a house, you know, you start looking at lenders and different loans and things like that, you're going to find that you're more than likely going to be compounded monthly, okay, or quarterly or something like that, versus, you know, if it's your own money, they kind of do the flip, okay? It's kind of reversed. It's whatever works in the best favor of the bank is usually what they have. So definitely shop around. All right, now we've talked about, you know, compounded annually, compounded quarterly, weekly, monthly, daily, whatever, all those different options. But there's also something called compounded continuously, and you'll notice that this is a different formula. Now, compounded continuously means like every microsecond in time, it's constantly recalculating. All right, well, when that happens, we use something called the PERT formula. And PERT is PE, so remember E in your calculator is second ln, so we talked about that a little bit ago. And then RT is actually raised up, it's an exponent, all right? But that's our formula, so it's the PERT formula for short. And what you're gonna notice is this example is the same scenario as the other ones. We're still depositing $6,000 for 12 years at a 9% interest rate, but it says what? Compounded continuously. All right, so compounded tells you it's compounded, obviously, but continuously is what's going to lead us to use the PERT formula instead of the compound interest formula. All right, so when we set it up in the PERT formula, we're going to say P, that's my principal, my starting amount, so $6,000. E, so E, remember, is a numeric value, so it's on your calculator, we'll show it again. And then raised to the RT, so 0.09, T is still 12, all right? So remember, this is an exponent. So in your calculator, we're going to type 6,000 E. Remember, we do that by doing second ln. If you have the black TI-36 calculator, you don't have to hit second. Yours is going to be the third button down, and I wish I had it to show you, but your third button down is going to have an E, and it's going to have like a box. So that will be the button you use. You don't have to hit second. It's like it's already a button, okay? So E is, and then notice it automatically pops us up, right? Which is great, because if you forget, then it's going to automatically like put you there. So 0.09 times 12. So $17,668.08 if I round it. So not a lot of a difference from like weekly. You know, you can see that it went up a little, not a lot, but you know, ultimately, if it's your money, I mean, hey, I could use an extra $16 or $17, right? Couldn't you? So the more often it's compounded, the better it is for you. All right. If it's your money and you're making interest, you know, like you're earning interest, I mean. All right, so those are some examples from that. I did want to flip over to page 8 and just do a couple of other examples just so that you have them. And then remember, page 9 is your homework assignment. So there's some extra problems on there for you to try. All right, so if you look at, let's look at number 2. All right, so number 2 says you buy a car for $17,000, but it's going to depreciate because it's going to go down in value, all right, at a rate of 16% per year. You pay off your car after 6 years, which that's great, good news, all right? But how much is it worth after 6 years? Maybe you're like, okay, I paid it off, I'm ready for something new, I want to sell it, all right? Well, the trigger word, the key word here is depreciates. That tells me what formula I need to use. All right, so let's kind of go backwards a little bit. Sorry to make you dizzy here. All right, but we learned in our other lesson that we have the growth model and we have the decay model. So remember, if you're going down in value, you're going to use this formula right here. If you're going up in value, you use this formula right here. And the difference is the plus versus the minus. So if I'm going down, I should expect to subtract. If I'm increasing, I should expect to add. All right. So when we flip and look at this example again, depreciate, that's going to tell me to use the decay model. So A times 1 minus R to the T power. All right, well, A is my starting amount. So $17,000. 1 represents 100% of your initial value minus 16%, 0.16. T is 6. All right. So that's how we're setting up our formula. Be careful. Common mistake is somebody's going to put 1 minus 16 instead of 0.16. So you can use the percent button. If you want to use 16, you could do 16%, or you can convert it to a decimal, which is what I typically do. All right. So in the calculator, I'm going to have 17,000, 1 minus 0.16 to the 6th power. So this car, I could sell it maybe for $5,972.07. So about $6,000 would be a reasonable selling price. All right, and you can use like Kelley Blue Book and some other types of things, but this would be kind of an idea if there was a model for that specific car. So you could probably look up, you know, decay models and things like that and maybe find something that you could use. All right, but that kind of gives you an idea. All right, so another example would be number 3. All right, you buy a home that costs $180,000 in 1998. If the home's value does what? Increases. That means it does what? it goes up in value by 4% each year. How much will the home be worth in 2010, which is like forever ago now, right? But the trigger word here is increase. It's going to go up in value. Do you see compounded anywhere? Nope. So we're going to use y equals a times 1 plus r to the t power. So that's our growth model. Now, A, we start out with $180,000 times 1 plus 0.04. Now, this is where people mess up. Like here, 16% was just 0.16. Here, 4% is not 0.4, it's 0.04. So you got to think about like money, like 4 cents would be 0.04, not 0.4. 0.4 would be like 40%. So be careful. And then how many years go by? Well, from 1998 to 2010, how many years go by? Should have said 12. All right. So let's see how much this house would be worth if it keeps going up, if it follows that same trend. All right. So we would say 180,000. Always double check your zeros because sometimes it's easy to like add an extra or take one away. 1 plus 0.04 raised to the 12th power. And we get $288,185.80 if we round it. All right, not too shabby, pretty good investment, right? And, you know, we talked about this a little bit in class, but obviously, you know, that number will obviously be influenced by, you know, just current housing market, you know, and trends and things like that, because, you know, sometimes the market's going to be hot and your numbers, your values of your homes are going to go up. But then sometimes it's not. Sometimes it's more of a buyer's market and you're not going to be able to sell it for as much maybe. So it just really depends. There's also other things that influence that, you know, environmental issues, just all kinds of things. I mean, you know, I think about like our current city, you know, what are they building in Locust Grove? Well, they're building a lot of warehouses. Well, I don't know about you, but I don't really want to buy a house that's right there with a big old warehouse in my front yard practically, right? So maybe that person couldn't sell for as much. Okay, so they may not gain value. They may actually have a depreciation. All right, but it really just depends on market trends, all kinds of things. All right, so let's look at another example. All right, so I'm trying to just pick and choose some from this page, not all of them. All right, so we have number 5. It says, determine the value of an account in which a person invested $8,500 for 10 years at an annual rate of 6% compounded, what? Continuously. So what formula do we use for continuous? The PERT formula. So we're going to use PERT. So P-E raised to the R-T. So PERT has an exponent, right? So our principal is the 8,500. So 8,500E raised to the RT. So 0.06, because that's my rate, 6%, times 10 years. All right, so remember these are exponents. So in your calculator, move this up a little bit. I'm going to have 8,500 second ln to get E, 0.06 times 10. And it would be $15,488.01 if I rounded. All right, so that would be a really good investment. Again, 6% is honestly not a realistic interest rate, you know, but it gives you an idea at least. All right, so one more example, and then I'll close off the video. All right, so if you look at number 1, flip this over. All right, in number 1, you deposit $2,000 into an account with a 5% annual interest rate. Find the balance after 3 years if the interest is compounded quarterly. Now that's not continuously, that's quarterly. So that means we're going to use the compound interest formula, which is P times 1 plus R over N to the NT power. All right, so that's our compound interest formula. So the principal is the $2,000, 1 plus my rate, So 0.05 over n. Well, n is 4 because quarterly happens 4 times a year. N is still 4. T is the 3 years. All right. So that's how we're substituting into the formula. So 2,000 times 1 plus n over d, 0.05 over 4, bump off, close your parenthesis, exponent, so raise it to the 4 times 3 power, and you get $2,321.51 if you round it. All right. And that's that. So tried to give you a few extra examples because at this point we've talked about 4 different formulas. We've talked about the growth model. We've talked about the decay model. We've talked about compounded interest. All right. We've also talked about compounding continuously. So 4 different formulas that you need to pay attention to what is being said in the problem itself. Okay. Things that people mess up on is their percents. So we a lot of times mess that up. Like we have like 5%, and instead of putting 0.05, somebody's going to put 0.5. All right, so just be really, really careful with that. Also, people mess up the zeros. So double check your zeros, especially if you're dealing with a lot of zeros. Like this 180,000 would be real easy to add a 0 or take away a 0. And then obviously that's going to impact your final amount. All right. So just be careful and go ahead and try those problems on page 9.